Okay, I would like to talk through this homework assignment, complex exponentials, phasors and signal processing. So I'm trying to relate complex numbers to signal processing, and you'll find out that roots of unity play a key role. First of all, I will go over this first part quickly because I went over it during the class session. Here, using calculus, I'm going to relate cis to the idea of complex exponential. Looking at derivatives, you find out that the derivative of cis acts very much like the derivative of a complex exponential. So you can find that out. So remember, cis has cosine and sine. The real part is cosine, the imaginary part is sine. And you can think of that as the as the x and y part of a circular motion. So I have included a link to a video that you can see that, how cosine and sine give you the horizontal and vertical components of a circular motion. This other part is just some notation. You have a frequency, where I guess frequency is 2 pi times frequency is 1 over the period. So omega is called the angular frequency. So 2 pi f is equal to omega. All right. Here I talk about negative frequency. When you have complex waves, you can have a negative frequency, and you're supposed to think about what that means in terms of circular motion. Okay. So here, if I do have a complex exponential function, you can actually express it in terms of what I could call the complex amplitude, a plus bi, and the phasor part, cosine omega t plus I sine omega t. So this is very similar to the phasor representation in the book. Okay. And now we digitize. We take the function and take samples. So if I have e to the I omega t, and I sample it with sampling period delta, well, when t equals 0, I get e to the 0, which is 1. When t is delta, I get e to the I omega delta. When t is 2 delta, I get e to the 2 I omega delta. So we get a series of values. If I also have an amplitude alpha, I get alpha times 1, alpha times e to the I omega delta, alpha times 2 I omega delta. And here again, alpha can be a complex number. All right, now in theory this is an infinite sequence, but it can repeat. So it assumes only a finite number of values. Here are some exercises related to these ideas. A, give an example of a complex signal which, when sampled with sampling period delta equal 1, gives the values 1, I, minus 1, minus I. In other words, when you put in time 0, you get 1. When you put in time 1, you get I. When you put in time 2, you get minus 1, and so on. Of course, you recognize these as the fourth roots of unity. Now, problem B, given that the signal frequency is omega, give a sampling period delta such that the sampling signal e to the I omega t takes values equal to the nth roots of unity. So when I say sampled signal, that means the signal at time 0, delta, 2 delta, and so on. Also, give n different values of alpha, such that the sampled signal alpha e to the I omega t gives the same set of values, not necessarily in the same order. Right? You might not start out with 1, you might start out with something else, but it gives the same values. It gives the same set of values. C, given the sample period delta and alpha equal 1, find all values of omega such that the nth sample is also equal to 1. Now notice, by nth sample, I mean the sample at time n delta. According to this convention, the sample at time t equals 0 is referred to as the 0th sample. Sometimes you get some confusion because The sample at time t equals 0 is the first sample in the list, but I call that the 0th sample. Those of you who've done programming with Python have seen this before. When you have an array, the first element is the 0th element. So this is a common problem in dealing with arrays. It's better to get used to this. You have the 0 indexing or you have the 1 indexing. So here we're using 0 indexing. The first sample is called the 0th sample. All right. Given the sampling period delta, give an example of two different frequencies, omega 1 and omega 2, that will produce the same samples. It's possible when you sample that two different signals will give the same result. And this is called aliasing. In fact, there are lots of frequencies that will give the same result. All right, so building on the previous exercise, give necessary and sufficient conditions on the frequencies omega 1 and omega 2, such that the signals alpha eta I omega 1t and alpha eta I omega 2t give exactly the same samples at the same sample times. Once again, use sampling period delta. All right, so this gives you some idea about digital signals. They're sines and cosines sampled at a particular regular frequency. For the remainder of this investigation, we will consider signals that are linear combinations of complex waves with angular frequencies 2 pi k f over n. Remember the relationship between angular frequency and frequency. This means the frequency would be kf over n, where k is from 0 to n minus 1. Here f you would call a fundamental frequency. So these are all multiples, or actually f over n. So these would all be called multiples of a fundamental frequency. Such a signal S of t can be written as a sum. S of t is the sum. So here we have linear combination, just means a sum of constants times these angular waves. And here this is missing an I. Well, it was missing an I. It's not missing an I anymore. All right, now the signal's information is in the amplitude. Okay, all of these amplitudes contain information. You can imagine that if I had some information, I could code it as amplitudes. Right? I could have A is 1, B is 2, C is 3, and so on. And for each letter, I could put a different amplitude. And I could use different frequencies, and I could code information in a signal like this. Now, that's a very simple picture. It's actually more complicated than that. But the idea is the same. You do have information, and you translate that information into numbers, and these numbers are coded as amplitudes. And I can also use different frequencies. And I want to be able to recover the amplitudes. Right? If I send information in terms of amplitudes, I want to be able to get the amplitudes back again from the signal. So you take the amplitudes, turn it into a signal, send the signal through the air, recover the signal on the other side, then take the signal and recover the amplitudes. That's what communication is all about. All right. So, exercise 5, give the smallest possible sampling period, delta, such that the complex wave e to the 2 pi I f t over n sample with period delta gives the nth roots of unity. All right. You're going to take this signal, sample it, and you want to get the nth roots of unity. You sample this signal. It turns out that properties of roots of unity will be crucial in obtaining a method to recover the amplitudes. To get at these properties, we'll have to bring modular arithmetic also into the mix. Okay, let zeta equal 2 pi I over n. So this would be called the fundamental nth root of unity. Right? You can see that this is basically the nth root of unity with the smallest angle, smallest argument. And recall that zeta to the k are the nth roots of unity. If you think about the 8th root of unity picture, all of the subsequent roots of unity are multiples of the first one. Since these are roots of unity, that means they're all solutions to this equation. Z to the n minus 1 equals 0. That's what root of unity means. It means you raise it to the nth power, you get 1. This means that the linear factors z minus zeta to the k all divide z minus 1. You know that if a number solves a polynomial equation, then this factor, z minus the number, will divide the polynomial. That's a basic fact of how you factor polynomials, right? All right, now, since we have n distinct roots of unity, we have n different linear factors. It follows that z to the n minus 1 equals z minus zeta to the 0. Zeta to the 0 is equal to 1. You know, any non-zero number to the 0th power is equal to 1. Times z minus zeta times z minus zeta squared, and so on up to z minus zeta to the n minus 1. If I multiply all these linear factors together, I will get z to the n minus 1. Okay? So I have a polynomial on the left-hand side and a polynomial on the right-hand side. So all the coefficients should be equal. All the coefficients over here should be equal to all the coefficients over here. So if you compute the coefficient of z in the right-hand side, show that the sum of the nth roots of unity is equal to 0. No matter what n is, whether even or odd, the sum of the nth roots of unity is always equal to 0. Okay? If you plot the nth roots of unity on a complex plane, that kind of makes sense. When n is even, it's easy to see. When n is odd, it's not so easy to see. But it is true that the sum of the nth roots of unity is always equal to 0. Very profound fact, actually. The product of the nth roots of unity is not equal to 0, but the sum is equal to 0. Okay? The product is actually equal to 1, if you think about the constant term. Right. So from proposition 3520 in the book, we have given a modular equation ax is congruent to c mod b, where a, b, c are integers, then the equation has an integer solution for x, if and only if c is an integer multiple of the greatest common divisor of a and b. So we're going to use this seemingly abstract proposition to prove something very important about signals. Okay. Use this proposition to prove the following. If k is greater than 0 and k is relatively prime to n, then for any integer m, where m is between 0 and n is not included, there exists an integer j such that zeta k to the jth power is equal to zeta to the m. Okay? So think about what this means. Any integer m in this interval and any k that's relatively prime to n, I can take the kth root of unity, raise it to the jth power, and get the mth root of unity. In other words, I can say that if k is relatively prime to n, then zeta to the k can generate all the other roots. Right? Problem 2, show that j in the previous exercise can be chosen between 0 and n minus 1, and that's inclusive. It could be 0, it could be n minus 1. Okay. Number 3, show that if k is greater than 0 is relatively prime to n, then the complex number zeta k to the j, and there should be another parenthesis here. So what am I thinking? There is a parenthesis. Okay, j is 0 to n minus 1 are exactly the nth roots of unity in rearranged order. Okay, so as I said, this kth root of unity does generate all of the roots of unity in some different order. And you can see some example. Well, I'll just talk through it. Suppose you take the fifth roots of unity, right? So the angles are 2 pi over 5, 4 pi over 5, 8 pi over 5, and then 10 pi over 5 takes you back again. Is that right? 2 pi over 5, 4 pi over 5, 6 pi over 5, 8 pi over 5, and then 10 pi over 5. All right, so those are the roots. The basic root of unity is 2 pi over 5. Now suppose you took the root of unity with angle 4 pi over 5. Take that root and multiply it by itself 5 times. And you'll see that you get all 5 of the roots of unity. All right? And it's true in general. You could also do the third fifth roots of unity and multiply that by itself 5 times, and you will generate all 5 fifth roots of unity. All right. But here so far we're just looking at the case where k is relatively prime to n. You can also take the case, say, with fourth roots of unity, and then take the second fourth root of unity, and you'll find that that does not generate all of the fourth roots of unity. All right. So there's this fact that k is relatively prime is key. Okay. So then, number 4, show that if k is relatively prime to n, then this sum is equal to 0. All right, and I do have the I there, so everything is fine. All right, now suppose k is between 0 and n, and k is not relatively prime to n. And here 0 is not included. Then show there is a number n prime, which divides n, such that the sum from j equals 1 to n prime of e to the 2 pi I j k over n is equal to 0. All right, so think about what happens when here you have k over n. Think about when k is not relatively prime to n, what happens when you take k over n? Show also that the sum from j equals 0 to n minus 1 of e to the I j k over n is equal to 0 by breaking the sum of n terms into n over n prime sums. Now, since n prime divides n, this is an integer, right? And show that each of these sums is equal to 0. So in other words, this larger sum is equal to 0 because it consists of smaller sums that are all equal to 0. So what have you shown? If k is relatively prime to n, then this sum is equal to 0. If k is not relatively prime to 0, the same sum is equal to 0. Okay, so in all cases, if k is between 0 and 0 is not included, you can think about what happens when k is equal to 0. In fact, that's the next exercise. But when k is not equal to 0, and you sum over j, remember here, this looks a little confusing. The I is a complex constant, the j is the index of the sum, and the k is a fixed number between 0 and n. And this sum is equal to 0. Okay, and this is extremely important identity. Someone pointed out that if you take n equal to 2, this gives you Eulers' formula, which is a very beautiful formula. So this generalizes Eulers' formula. Okay, previous equation gives 0 when k is between 0 and n. What happens when you get k equals 0? Okay, so why in the world did we go through this? Remember that we wanted to recover the amplitudes in this signal. So that's our task here. We have this signal, and we have these samples, and we want to recover these amplitudes. So here's where some magic comes in. Okay. So here it says, using the sampling period delta equals 1 over f, so the amplitudes alpha k can be recovered from the samples by multiplying the consecutive samples with the consecutive terms of this sequence. E to the minus 2 pi k, that should be an I there. Whoops, there it is. Okay. Sometimes this can be confusing because here we have an I, which is a constant, and the k and the j, which are indices. What makes it more confusing is the engineers use j instead of I as their complex imaginary number. So you can be warned about that. You might see 5 plus 6j in the engineering textbook instead of 5 plus 6i. Well, that's the problem with translation. The engineers are probably French anyway. Okay, so all right, so I lost my train of thought. Using sampling period delta equal 1 over f, so the amplitude alpha k can be recovered. This is our holy grail that we want, can be recovered from the samples by multiplying consecutive samples with the consecutive terms of this sequence. Now notice here I'm using a minus sign. All right, so I take the samples, multiply by this, and sum the result. Okay, and here I'm using a particular sampling period. Okay, using digital signal processing, it's easy to multiply signal samples together and add them. All right, so here the process that I would have to use to recover these alphas is to multiply the incoming signal by another set of numbers. And that's quite possible using amplifiers. So that's one of the great things about signals is you can manipulate them so readily. All right, you might think complex multiplication is difficult, but it's not, because we have the real and imaginary parts in separate channels. So as I was trying to say, the real and imaginary parts really are sent separately. So we can multiply the real and imaginary parts separately and add them without any problem. So in fact, what you've just derived is the complex form of the famous discrete Fourier transform. And discrete Fourier transform is the same thing as Fourier series. It's difficult to underestimate the importance of the Fourier transform in modern mathematics. It pops up everywhere, even in number theory. So this is one of the great innovations of mathematics. Not only is it theoretically extremely interesting, but it's also practically extremely useful. And one of the members of the class is actually working on a problem for finding roots of general polynomials, and it uses this discrete Fourier transform. So it pops up everywhere. All right, that's it.